130 is a study of multivariable calculus. First year, you studied functions of one variable, f of x. You learned how to differentiate them, you learned how to integrate them, you talked about a number of their applications. In this course, we extend that to talk about functions of more than one variable. If you had a function of two variables, it would be denoted something like this. If you had a function of three variables, it might be denoted by that. So this is a function of x and y, and this is a function of x and y and z. Instead of finding here the derivative, or say a definite interval, in here we talk about partial derivatives of that function with respect to x and y. We also talk about the double integral of this function in the xy plane. For this one, we would talk about partial derivatives with respect to x and y and z, and we would talk about triple integrals of that function in some volume of space. Visualization is important to most of us. I'm a visual person, and most other people are visual as well, but not everybody. If we can see a picture of what's going on, we can usually get a better appreciation of the ideas than if we simply talk algebraically. We did that in first year. When you had a function of only one variable, you set it equal to y, and its visualization was a curve somehow in the xy plane. And you use that a lot in this visualization. You talked about tangent lines to that curve, you talked about relative maximum minima, you talked about global maximum minima, you talked about area under the curve, and you talked about various other applications of that single variable calculus. We want to do the same thing for a function such as that. If we've got f of x and y, we put z is equal to f of x and y. What we now draw, and we'll see in a moment, that if we draw it graphically, is a surface in space. And so we visualize in this function geometrically as a surface. If you give me a function of x and y and z, I have a bit of a problem. If I put that equal to u, and I want to draw that, now I'm in force space, and I have a little trouble visualizing force space. So what we often do is introduce ideas for multivariable calculus in terms of functions of two variables so we can visualize and get appreciation of the ideas geometrically as well as algebraically. We don't have the geometry for this, but when we talk about it, we can usually think about the two variable problem in order to get the ideas across for a three variable problem. I said that if I'm going to draw this, it's going to be a surface, right? I want to show that to you. So first of all, let's talk about coordinates. In section 11.1, it talks about rectangular coordinates in space. When I draw space, I can draw it like this, x and y and z axes, and this you've seen before when you're talking about geometric ideas in 1210 perchance. Right? This is what is called a right-handed coordinate system as opposed to a left-handed coordinate system. Nobody uses a left-handed coordinate system. I've only seen one book in my whole life that did that, and I don't know why the person did it. By a right-handed coordinate system, you mean if you curl your fingers from the x-axis towards the y-axis on your right hand, then the thumb will point to the positive z-axis. Right? So we will always use a right-handed coordinate system. When you talk about points in space, using this right-handed coordinate system, every point has a set of coordinates, three of them, x-coordinate, y-coordinate, and z-coordinate. And there's two ways that you can look at what these coordinates mean. One way is to say that x, you want to know, let's talk about the z, probably the easier one. You drop a perpendicular down to the xy plane. So that point is in the xy plane, and that is z. If you want to talk about the x-coordinate, you drop a perpendicular to the other plane, the yz plane, you drop it back there till it hits, and that's the x. And similarly, the y, you drop a perpendicular to the xz plane, and that's the y. That's one way to look at it. Another way to look at it is to take this, do that with the z, but then down here you draw a line parallel or perpendicular to the y-axis, or to the x-axis, and you draw a perpendicular over the x-axis. And this is the x one here, and this is the y one here. Either way, they're equivalent. It depends upon what application I'm talking about, which way I would like to look at the x and the y and the z. If you give me 2 points, P1, with coordinates x1, y1, and z1, and you give me another point, P2, x2, y2, and z2, we talk about that line that joins them, and we want to talk about what come up will be the length of that line. And you've seen it before, that the length of that line is the square root of x1 minus x2 squared, y1 minus y2 squared, plus z1 minus z2 squared. It really comes from Pythagorean. You kind of draw a box with that P1, P2 as a diagonal, you get that distance. Right? So that you've seen before. And that's all that's really in section 11.1. Should mention this is called a Cartesian coordinate system. You have seen one other coordinate system when you're talking about the xy plane. You saw in first year polar coordinates. You saw them in 2 contexts. You drew curves in the calculus course, and in the 1210 course, you use them in the complex plane Cartesian coordinates, and then you switch to polar coordinates for the polar representation of a complex number. In this course, you're going to see 2 other coordinate systems, not for the xy plane, for xyz space. A coordinate system called cylindrical coordinates and a coordinate system called spherical coordinates. They turn out to be more efficient in solving certain problems, in particular when you're solving triple integrals. Visualize again, I said, is important because one of the problems I'm going to give you later on is I'm going to describe to you some surfaces, and these surfaces are going to enclose some kind of volume, and I'm going to ask you to find that volume. If you can't draw it, I would defy you in general to be able to figure out 6 limits on the triple integral. Algebraically, some people can do it. I just don't happen to be one of them. And when I read what they say, I don't think most people understand what they're saying. But if I draw a picture, I'll be able to tell you how to get those limits on that triple integral in a very nice geometric way. That's basically what's in section 11.1. 11.2 embarks upon this idea that we're saying that if we want to talk about functions of 2 variables, we need to be able to draw surfaces. So we want to practice drawing surfaces, much like you did in first year. First year, probably, if you didn't, if you got it in high school, you might have had a review in first year of drawing curves. How do you draw curves efficient ways? So section 11.2 talks about curves and surfaces. For instance, suppose all right, so a bunch of examples, but let's take ones you have seen before, linear equations in. So this is going to be surfaces in x, y, z space. Linear equations in x and y and z. Equations of the form ax, by, cz plus d is equal to 0. Some people prefer to put the d on this side. It doesn't really matter. You learned in 1210 that every linear equation in x and y and z describes a plane, not just a surface, but a plane. For instance, z equal to 0. What does it describe? It's a very special one. That's a 1, that's a 0, that's a 0, that's a 1, and that's a 0. That says all the points in space whose xz coordinate is equal to 0. That means the xy plane. That is what all the points in the xy plane, their coordinates satisfy z equal to 0. So the coordinates would always be an x and a y and a 0. And similarly, if you've got x equal to 0, that describes the yz plane. And similarly, y equal to 0 describes the xz plane. Those ones are easy. What if I gave one that's not so easy? Say x plus 2y plus 3z is equal to 6. Still linear, therefore it's still a plane. And you learned in Call 10 that a nice way to draw this one would be to do the following. Find its intercept on the x-axis and the y-axis and the z-axis. If you want to know where this plane crosses the x-axis, along the x-axis, y and z are both 0. So you put y equal to 0, you put z equal to 0, and you get x is equal to 6. You want to know where it crosses the y-axis, you put the x and the z to be 0, and you get y equal to 3. And similarly, as the intercept with the z-axis is 2. So those have got to be 3 points on the plane. But if those are 3 points on the plane, then you really know what the plane is. If I join these 2 points, and I join those 2 points, and I join those 2 points, and visualize that triangle, and extend it in all directions, then that is what that equation describes, that plane. So you've seen those ones before. Consider somewhat different, however. So let's consider example. So those ones you've seen again before. Example 1, suppose I give you the equation x squared plus y squared is equal to 4. Now, I can't just give you that equation and ask you what it describes geometrically unless I tell you where I want to be. That is, do I want to be talking about that equation in the xy plane, or do I want to be talking about it in xyz space? And it is different. If I want to talk the xy plane, everybody knows that describes a circle in the xy plane of radius 2 centered at the origin. But what if I'm in space? Well, certainly ever that circle that was there, that circle is this circle, and all those points on that circle satisfy that equation. Everybody on this circle has an x-coordinate of something and a y-coordinate of something and a z-coordinate being equal to 0. And if x and y satisfies this equation, then that point is on this circle. But that equation says nothing about z. And don't get the idea that if it says nothing about it, it means it has to be 0. Nothing could be further from the truth. The fact that z isn't mentioned means that z can be anything. So that means if you took that point and you drew a vertical line through it, then every point on that vertical line would satisfy this equation. Because this equation doesn't demand anything about z. But that x and y coordinate of that point are the same as the x and y coordinates of that point. Well, you can't just do it with that point. You can do it with any point. So if you take any point on this circle and you draw a vertical line, what are you going to get? You're going to get a cylinder. So this equation then describes a cylinder if we are in space. Different than if we're in the xy plane, in which case it becomes a circle. What if I give you this example? So example 2. X squared plus y squared plus z minus 3 squared is equal to 16. Well, at first this might seem very complicated, but if you thought about, remember we had on the board here, and I erased it, the distance between 2 points in space. I remember that form, x1 minus x2 squared, y1 minus y2 squared, z1 minus z2 squared. Right? Well, suppose I draw here 2 points, x, y, and z axes, and I put the point 0, 0, and 3. And I take another point with coordinates x and y and z. And I want to know what this equation demands about that point there. Where does it have to be? Well, is not this the square of that length? If I asked you to find this length, then you'd say this one minus this one squared, that one minus that one squared, that one minus that one squared, and you'd get exactly this. And it's saying, all the points you want to talk about demand that this thing be equal to 16, or the square root of it be equal to 4. So it means this point wanders around in space so that its distance from to here is always 4. What does that mean you got? You want all the points that are the same distance 4 from this guy here. Would that not be a sphere centered at that point of radius 4? And indeed that's true. This thing describes a sphere of radius 4 centered at 0, 0, and 3. So although that will look rather complicated, if we happen to recall that distance formula, it's not so bad at all. Well, let's take a few more before we draw any conclusions about what equations in x and y and z represent. Suppose I give you 2x plus y equal to 4. Example number 3. 2x plus y is equal to 4. And the first thing you should note is that no z. Second thing you should note is that it's linear. That's a linear equation, right? Which means, therefore, it's a plane. How do you draw it? Well, the fact that there's no z here would prompt me to do the same thing that I did in this example. Draw this, whatever it is, in the xy plane. But that's a line in the xy plane with an x-intercept of 2 and a y-intercept of 4. And so that is the line. And all points on this line satisfy that equation. But again, z, no restriction, so lift that line in the z direction. And what do you get? A plane. A vertical plane standing on that line. So a vertical plane. All right. Next one. Example 4. Z is equal to x squared plus y squared. One of the most useful techniques in drawing surfaces is to take cross sections of the surface. For instance, if I took, say, a plane and I slice through this surface, whatever it looks like, I'm going to get a curve. In particular, if I slice it with the xy plane, the equation of the xy plane is z equal to 0. So if I put z equals 0 along with this equation, this would tell me how the surface, whatever it looks like, intersects the xy plane. But if you put z equal to 0 here and you put it there, you'd have 0 is equal to x squared plus y squared. And the only point that satisfies that is x equals 0 and y equals 0. So whatever this surface looks like, it cuts the xy plane in one and only one point. No other point in the xy plane can satisfy this equation. Only that. So that's a cross section, but it didn't lead to too much. What if I do a cross section with the yz plane? The yz plane has the equation x equals 0. So if I put those together, this would represent how this surface intersects the yz plane. But if you got x equal to 0, then z is going to be equal to y squared. That part's going to go away. And you know that that's a parabola. So whatever the surface looks like, it intersects the yz plane in a parabola that opens upward. So it would look like that. Well, you have to visualize that that parabola is in the yz plane. Well, if I can do that, I can also put y equal to 0. In which case I would have, along with z is equal to x squared plus y squared. and I would get z is equal to x squared. So this is supposed to be how it intersects the xz plane. But again, that's a parabola. So you draw this parabola. Right? That parabola was in the yz plane. This parabola is in the xz plane. One looking like this, the other looking like that. Now those cross sections are supposed to suggest to you hopefully what this surface might look like. Can you think of anything that if you cross-sected it, all right, you get a parabola this way, you get a parabola that way, and you don't get anything down here except the origin. And what comes to mind is that maybe it's a bowl that opens up forever. Maybe, okay, and for a bowl, would you not agree that if I cross-sected it, cut it with a plane up here, it would produce a circle. Getting ever larger and larger and larger as I take cross-section higher and higher and higher. So if I could prove this, I think I would have guaranteed myself that I've got myself a bowl. So if I want to cross-section it this way, I would be taking planes z equal a constant. So let's do that. Let's intersect this surface with a plane parallel to the xy plane and above it by putting z equal to k greater than 0, along with z is equal to x squared plus y squared. Well, if you do that, you can put this into here, and then x squared plus y squared is equal to k. Is that the equation of a circle? And the answer is yes, it is. So we've just verified that, and as k gets bigger and bigger and bigger, this is really the square of the radius, right? That the radius of that circle is bigger and bigger and bigger. I think we verified indeed that that equation describes a bowl. All right? So this idea of cross-sections can be very useful. So let's do a couple more examples. Suppose I gave you example number 5. Z is equal, I'm going to do y equal, just to change it, the square root of x squared plus z squared. Don't want you to think that I always have to have z equals, z equals, z equals, z equals. We can interchange those. Let's try this same idea. Cross-secting it and looking at these cross-sections and see if we can think of what the surface might be. So if we cross-sect it with the xy plane, right, we would put z equal to 0, along with y is equal to 3, the square root of x squared plus z squared. And you put z equal to 0, that's going to lead you to y is equal to 3 times the square root of x squared. And what's the square root of x squared? Don't tell me it's x. It's the absolute value, right? It's 3 times the absolute value of x. So we're saying, if you go to the xy plane, how the surface intersects the xy plane is in this curve. And you all remember from first year, that's a V shape like that. So visualize then, that's a V in the xy plane. Let's do the same thing by putting x equal to 0. If we put x equal to 0 along with y is equal to 3, the square root of x squared plus z squared, then we can say that y is equal to 3, the absolute value of z in a similar way. What's that? That's another v. This v is in the yz plane. So you have to visualize, right? It's up here and it's down there. So you look at that picture and you really can't see, if you look at that picture, what's going on. You have to have the visualization in your mind and then say, does that picture kind of agree with the left? But you can't look at it and say, I can see what you're talking about. No, that does not work. But remember, you've got a V in the xy plane and you got a V in the yz plane. Well, if you intersect it with the xz plane, that means you put y equal to 0. If you put y equal to 0, all you get is this 1 point, 0, 0, and 0. So now you ask yourself, what possibly could this somewhat like this. Right? Here we guessed a bowl. You can't say bowl here because it's got these straight edges rather than these parabolic things that went like this. These ones are straight. What might come to mind is, how about a cone? That if you do here, if it was a cone that came this way and you cross-sected it with XZ planes, you would get circles. So let's ask them, is this indeed a cone? Right? Because if it were, you can see that indeed you get this V shape for a cross-section and you get this other V shape for a cross-section. How would we verify it? Well, if that is indeed a cone, we're saying that any cross-section parallel to the XZ plane out here is going to produce a circle. So let's now put in y equal to a constant greater than 0, along with y is equal to 3, the square root of x squared plus z squared. But now then you have k is equal to 3, the square root of x squared plus y squared. If you square that, you get x squared plus y squared is equal to k squared over 9. Is that a circle? Yes, it is. Radius of the circle? K over 3. So indeed we verified that this equation does describe a cone around the y-axis. Okay? Again, cross-sections have led us to that. Here's one that turns out to be very difficult for most students when they try and draw it. Cross-sections are going to help, but it's which cross-sections you look at determines how or if it helps. So consider this next example, number 6. Y is equal to z plus x squared. We're going to try and see if we can draw a surface that results from this equation. Thinking again that had this surface. All right. So which cross section would you like to take? Well, I think a natural one would be one with the YZ plane, because that'll kill out the ugly piece, which is the x squared. So if we put x equal to 0, along with y equal to z plus x squared, we get y is equal to z from the two of them. So that means you're in the YZ plane, and you've got this, but that's a line. Here, I'll draw, right? There's another one back here, right? So you have to visualize that line in the YZ plane, tilt it up at pi by 4 radians. Don't tell me 45 degrees, because I don't like that, right? So there's that intersection, okay? What else might we try? Well, if we try putting, say, z equal to 0, along with y is equal to z plus x squared, then we get y is equal to x squared. Right? Y is equal to x squared. So this is in the xy plane, right? And yet y is equal to x squared. All right? So y equal to x squared. So in the xy plane, well, that's down here. Y is equal to x squared. That looks like that. A parabola. All right. So I've got this straight line in the YZ plane. I've got this parabola in the XY plane. Well, if we wanted to try the last one, we would put y equal to 0 for the cross section with the XZ plane. So if we do that, then we get z is equal to minus x squared. So we go to the XZ plane, and we draw a parabola that opens downward. Down. All right. So, can you visualize a surface in space that would do this? And the answer is, well, probably not. In other words, I haven't chosen cross-sections that are really, really helpful. But notice in the other two examples, we kind of surmised what it looked like, and then we kind of verified what it looked like by taking a whole bunch of cross sections. In that first one, the bowl, we took cross section this way. In the cone, we took cross section this way. Right? I'm going to suggest here that we put z equal to k. We're taking then horizontal cross section. We're slicing through this surface with z equal constant planes to see if we can see what it is. So if we do that along with z plus x squared, then we get y is equal to k plus x squared. So it says when you're up here, or you could be down here, let's visualize up here first, and you slice through this surface with this plane, you get this. So that is in this plane, but that's a parabola, right? Right? It's precisely this parabola we have here, but it's shifted, all right, k units in the y direction. So up here in this plane, you get this parabola that's shifted. Would that parabola hit that point on that line? So visualize this plane passing through that point. Is that what this parabola would look like? Would it be exactly this parabola, but shifted over there? And it might take a couple of minutes to convince yourself, but that's true. And it's not just that one. Any, take that point, draw the same parabola through it. Ah, now I'm getting an idea of what this surface looks like. Not the easiest thing to draw, but you've got this line, and through that line you have these parabolas. All these parabolas are horizontal. Can you visualize this surface then as something that looks like that? Right? Coming around or emanating from that line. Not the easiest one to visualize, but I think we've got exactly what it looks like. All right. Next one. Suppose one is to demonstrate the use of cross sections in an attempt to visualize what the surface looks like and then to verify it with further cross sections. Suppose I were to give you this one, example number 7. Z is equal to 1 minus 2 times the square root of x squared plus y squared. Well, if you kind of thought about it, right, the idea for this example is what I call building the surface. Building it from something I know. For instance, if I take away the 1, and I take away the minus 2, and I looked at that, that would be exactly the same one that I had here of a cone. That would be this cone sitting here. That would be a picture of that. Z is equal to the square root of x squared plus y squared. If you don't agree, or you don't believe me, then do some cross sections to verify that. Cross section this way giving V, cross section this way giving B, cross sections this way giving circles to verify a cone. So we recognize that one, and now we're going to start with that. Question is now, what does the 2 do? Forget the minus sign for a second. What does the 2 do? Right, if you put a 2 there and look at that, what does that do? That simply doubles all the z coordinates. Are you still going to get a cone? The answer is yes. Right? So that's still a cone, and if I don't put scales on here, you can't tell whether it's that one or that one. It represents both of them. Well, what does the minus do? I put a minus here now. Well, now all of the z coordinates on this surface are the negative of this one. That simply turns this cone upside down. And now finally, so that's that one, that's that one. 1 minus 2 square root x squared plus y squared. What does that do? It now adds 1 to all of these z coordinates on the cone. Isn't that going to take that cone and shift it up 1 unit? So the final picture is cone opening downward, starting at 1 there. So there's our final picture of what this surface looks like. Again, I built it. I started with this I knew. I incorporated the 2. I incorporated the 1 minus, and I incorporated the 1 to get the final picture. So I didn't have to go at it cross sections, right? I was able to build it because I knew the cone. One more building idea. Suppose I give you this one. Example number 8. Z is equal to the absolute value of 2x minus y. You could take cross sections here, but I'm not sure that you would be able to put them together properly. So let's do this idea of building. Let's first of all say, forget the absolute values. Let's draw it without the absolute values. Let's look at z is equal to 2x minus y. And what's that? That's linear. Therefore, it's a plane. It's a plane. All right, let's draw the plane. Now, this was a little more difficult to draw than the other. Remember, I had on the board once upon a time the plane x plus 2y plus 3z is equal to 6. And to draw that plane, we found its intercepts with the x and the y and the z axis. Therefore, got 3 points. We joined and said, there it is. Here, if you go for the intercepts, what are they? What's the x-intercept? The x-intercept. You put y and z equal to 0. You get 0. All 3 intercepts are 0. It goes to the origin. It doesn't give you 3 points. But notice, if I put z equal to 0, right, along with this, then I'm going to get 2x minus y is equal to 0, which is y is equal to 2x. Which means whatever this plane looks like, it cuts through the xy plane in this line, y is equal to 2x. So visualize that line in the xy plane. So the plane that I'm looking for contains that line. All right? It contains that line. Now, I could get another point on it and join, but let's just kind of visualize a plane, because I don't care really what it looks like. A plane that contains that line. It's going to have a slant to it. It's not vertical. It's not vertical because it's got z's in it, right? So it's slanted. So there's that plane. Now, what did the absolute values do? They should be saying, z, you cannot be negative. So any points on this plane where the negative z coordinate gets turned upside down. What does that mean? So if these guys are up over here and these guys are down, these guys will get turned up. So what are we going to get? A trough. All right? We're going to have a trough here. It's going to go up here, and down to there. We're going to get this trough. All right? This is the bottom of the trough, and then it's got some kind of slant, which I don't care about. It's producing a trough. So I was able to build that one again. Right? All right, let's think about all the ones we've seen. Would you agree that what we seem to be saying is that one equation in x and y and z will describe a surface? We also seem to be suggesting, let's put 2 equations down, right, that you're going to get a curve. Now, we've always taken, when we did the 2 equations, we always took something very simple, like z equal to 0, y equal to 0, x equal to 0 to get cross sections, but we put that thing, which is a plane, together with the surface to produce a curve of intersection of the surface with that special plane. That's what we seem to be suggesting. And in general, that is true. It's not always true, right? You don't get the idea that every equation in x and y and z has to represent a surface. Well, that's not quite true. Let me ask you this. Could you come up with an equation in x and y and z which would not be a surface? Can you come up with one? How about this one? X squared, y squared, z squared. If I put a 1 here, what's that? That's a sphere of radius 1, center of the George. What if I do this? A sphere of radius, I don't know. In other words, there is no point on this. Right? There's no point in x, y, z space that can satisfy that equation. So this describes nothing. What if I put it equal to 0 instead? Now it doesn't describe nothing, but it doesn't describe very much. There's only one point that satisfies that equation, and that's the point 0, 0, and 0. So that equation then, x squared plus y squared plus z squared, is only satisfied by that one and that one and only point. What if I change it to this? Z squared plus y minus x, all squared equal to 0. What does that describe? Well, if you have this, then you have to have z equal to 0, and you have to have y is equal to x. What's that? What's that? That means you're in the xy plane, and what have you got in the xy plane? A line. So this one is a line. So you can see that it's not true always that an equation in x and y and z has to describe a surface. It might describe nothing at all, it might describe a point, and it could describe a line, or I could make this into a curve. If I put that thing, a square there, this becomes a square, turns out to be a parabola. Right? But in general, one equation in x, y, z will describe a surface. You put two equations together, then what we're expecting is, based upon these examples, that you'll get a curve. So let's take a couple examples. Right? Suppose I give you then x squared plus y squared is equal to 1, and x plus y plus z is equal to 2. So this is an example. We're up numbering. Okay, so whatever that number is. Example. So there's two equations in x and y and z. This one's got all three variables. That one's only got two. Well, you know what this one is. We've already talked about that idea. That's a cylinder that stands on the circle, radius 1, in the xy plane, so pull it. There's the cylinder. What does this one represent? Answer, it's a linear equation. It therefore describes a plane. It has intersections. All three of the intercepts are 2. So it cuts here at 2, cuts here at 2, cuts here at 2, and if you join those and extend that triangle in all directions, you will get a plane. And what you're asking is, what are all the points that are on both surfaces simultaneously? Well, visualize that this plane is slicing down through this cylinder. Is it not going to therefore produce a curve on that cylinder, which you'll have to use your imagination, looking somewhat like this? Right? Slanted, right? So that curve is on the cylinder and it's on the plane as well. Right? It's a circle that would project down onto this circle in the xy plane. So two equations again, curve of intersection of the two surfaces. One last one. Z is equal to (4 minus x squared minus y squared) along with z is equal to x squared plus y squared. Now, this would be a favorite one later on. I say, go find the volume of the surface, of the volume bounded by these surfaces. Well, you know what this one is. We've already talked about him today. He's a bowl. There he is. A bowl that opens up. What's this one? We could build it. We could start with z equals x squared plus y squared, introduce the minus. Right? That thing is that thing turned upside down. And then what do you do to it? You shift it up 4. So you'd have this, that same bowl coming down from 4. And you're asking, what are all the points on these two circles simultaneously? What do they intersect in? And I think it's reasonably clear here. It's going to be, I believe, a circle. You've got a bowl coming down and a bowl coming up, and there's going to be a circle intersection of these two bowls. In fact, I'd be willing to believe that that circle is going to be horizontal. It's not going to be slanted up like this or that. It's going to be a horizontal circle. Well, that's true. I should be able to prove it. Well, notice if you took these two and said, oh, suppose I take these two equations and I eliminate the x squared plus y squared by saying put into here, take this and put a z in here, and z is equal to 4 minus z, which means that 2z is equal to 4, which means z is equal to 2. Aha! Is that what this is saying? That whatever this circle is, it's in that plane. Is it reasonable that it should be in a plane that is halfway between here and here? And the answer is definitely. And the equation of that circle is x squared plus y squared is equal to 2. Its radius is root 2. This is a better description. Let's say an easier description. So this is equivalent to that. Instead of saying that this curve is the intersection of those two bowls, you could say it's the intersection of this plane and that cylinder. Easier way to look at it, right? So again, one equation, surface. Two equation, curve of intersection of the two surfaces.